Welcome to Chapter 1 of our Bayesian Optimization series. In this chapter, we'll explore the fundamentals of this powerful optimization technique that's revolutionizing how we solve complex black box problems. You'll learn how Bayesian optimization enables intelligent, efficient search for optimal solutions when traditional methods fall short. A black box optimization problem is one where you can't see inside the relationship between inputs and outputs. Think of a chemical reactor where you adjust temperature, pressure, and concentration, but you don't have a formula to predict the yield. You can only run experiments and observe results. These problems have four key characteristics. The objective function is unknown, each evaluation is expensive and time-consuming, gradient information isn't available, and measurements contain noise. Let's look at a concrete example: optimizing a polymerization reactor. We have three parameters to tune: temperature ranging from 300 to 400 Kelvin, pressure from 1 to 5 bar, and catalyst concentration from 0.1 to 1 moles per liter. The response surface shows complex interactions between these variables. Starting from suboptimal conditions with a yield around 52%, Bayesian optimization can help us find the optimal conditions, reaching yields near 89%. All while minimizing the number of expensive experiments needed. The core of Bayesian optimization is sequential design. Unlike random sampling, which scatters points everywhere, sequential design learns from each observation to intelligently choose where to sample next. The comparison is striking. With the same 13 evaluations, sequential design achieves 23% better results than random sampling. Each new sample builds upon previous knowledge, progressively focusing on the most promising regions of the search space. The most critical concept in Bayesian optimization is balancing exploration and exploitation. Exploitation means focusing on areas where we expect high performance based on current knowledge. Exploration means investigating uncertain regions where we might discover something even better. The upper confidence bound, or UCB, combines both by adding predicted value to scaled uncertainty. This balance prevents getting stuck in local optima while still making progress toward the global optimum. Bayesian optimization follows a four-step loop. First, we build a surrogate model, typically a Gaussian process, to approximate the objective function from our observations. Second, we calculate an acquisition function that quantifies how promising each potential point is. Third, we select the next point by maximizing this acquisition function. Finally, we evaluate the objective function at this new point and update our model. This loop continues until we converge or exhaust our evaluation budget. How does Bayesian optimization compare to traditional methods? Grid search systematically covers the space, but wastes evaluations in unimportant regions. Random search is more efficient, but still doesn't learn from previous observations. Bayesian optimization outperforms both by intelligently focusing resources. In our experiments, BO reached the best objective value within 30 evaluations, while grid search would need well over 100 evaluations to cover the same space, and random search converged more slowly. Monitoring convergence is essential for knowing when to stop optimization. We track four key metrics. Cumulative best value shows overall progress, improvement per iteration reveals if we're still making gains, optimality gap on a log scale shows how close we are to the optimum, and convergence rate indicates when improvements have effectively stopped. When the improvement drops below a threshold for several consecutive iterations, we can confidently declare convergence. One of the most popular applications of Bayesian optimization is hyperparameter tuning for machine learning models. Consider tuning a random forest with parameters like number of estimators, maximum depth, and minimum samples for splitting. Starting from default settings with an R-squared score around 0.86, Bayesian optimization can automatically discover configurations achieving 0.92, a 7.8% improvement. This same approach applies to tuning PID controllers or optimizing any parameterized system. Let's recap what we've learned. Black box optimization handles expensive, unknown objective functions. Sequential design dramatically outperforms random sampling. Balancing exploration and exploitation is key to finding global optima. The four-step optimization loop systematically improves our solution, and Bayesian optimization outperforms grid and random search methods. Coming up in Chapter 2, we'll dive deep into Gaussian processes, the mathematical foundation that makes intelligent uncertainty quantification possible.